So exam 1 is Tuesday. What would that be? The 11th? Ooh, 9/11. And the topics on that will be the stuff on the introduction, problems related to those introduction problems. And second, the first law of thermodynamics, excluding the last one. We're going to lump that one in with the next topic that we go into. I think that's number 11, but I just don't remember exactly. I'll put that in detail on D2L. And okay, so there's supposed to be a quiz today. I'm going to try not to skip any more quizzes, but I am skipping this one. But don't feel like you studied for nothing, you know? Feel like you studied, and every time you study, the only reason that I want you to study is to get this material in your brain, you know what I mean? So, yes. Oh, yeah. That's a good, I like that. So let me show you a previous quiz. So here's the first quiz from last year. First law of thermodynamics is conservation of what property? The answer is energy. Define a property. Well, these are good questions. I could have given this quiz today. You know, so properties are the individual traits, the individual things that make up a state. Like right now, I'm sitting down. I don't know. I have zero velocity. I have a temperature of 98.6. And if you take all those things, it makes up a state that defines me at that instant. What are 3 ways energy can be transferred through heat? We haven't talked about that yet, but that's the next topic that we'll do after this. And I believe you had a question that was related to this one, right? In general, what's the relationship between the direction of forces in a force field and the direction of increasing potential energy? So a force field, so conservative forces, forces that where if you're given the location of the object, you know that's enough to specify the force. Those are associated with potential energy functions. And also, those are things that you can think of as a force field. A force field, like, what does it mean if you're in a beautiful poppy field? It means wherever you go, there's a poppy there waiting for you. Like, more drugs. Whatever. I can make so many drugs in this field. And not really. But that's the same idea as a force field. A force field just means wherever you go, there's a force there sort of waiting for you. You can think about it that way. So think about all these like gravity forces waiting in space for this stapler. I don't know why I could do this. So wherever you move the stapler to, you can think of it as activating the force at that place in the field. Okay, so that's the idea of a force field. Okay, so let's think about the relationship between gravitational potential energy and gravitational force field. gravitational force field is as simple as it gets. No matter where the stapler goes, there's a force of mg pointing down, waiting for it. You know, the potential. So if you, so how does it word this? What's the relationship between the direction of forces and increasing potential energy? Okay, so which way? So starting here, which way do I have to move the stapler to cause an increase in potential energy? Up, yeah, because potential energy function, gravitational is mgh, so you have to increase h, okay? So up increases potential energy. How does the direction up relate to the direction of the force? It's opposite because the force direction is down, and that's always the case. In sort of a loose way, you can think about it like this. A force field is always trying to push things towards lower potential energy. Okay. Technically, the correct thing, to say it correctly, if a thing starts at rest and the only thing acting on it is the force field will move it to lower potential energy. Okay. And that's true if any of you have taken circuits, or I guess you talked about this stuff, the people who've taken physics 2 already. It's the same thing with the potential energy in electric fields. You know, when you're talking about voltage and stuff, any kind of potential energy function is in that same way trying to push things to lower potential energy. All right, and that's the last question on that quiz. So anyone have any questions about those? It's not those specific questions, I think, that's maybe useful as much as just a sense of like what kind of things I'm looking for that I'm saying in notes. Yeah. No, the exams are all going to be problems like the practice problems, like the assigned problems. And the quizzes are going to be, so the quizzes are trying to make sure that you're reading and trying to remember what I say in lecture, and the exams are trying to make sure that you understand the problems. And I think I said this before, but when are you ready for the exam? This makes sense to me. Let me know if you need clarification. But you are ready for the exam if you could go to any problem on the exam that's going to be of the topics that are covered on the exam and explain to someone else how to do those problems. And if they ask you questions about why you did this and why you did this, you can answer those questions. If you understand the entire thought process for all these problems, then you understand everything that's going to be on the test. You know, there might be different ordering of sort of thought processes or whatever, but I think you'll find you could almost take the exam questions and say, okay, that one is mostly like this one, this problem that I was assigned, and this exam question is mostly almost totally like this problem that was assigned. You know, you'll see a real relationship if you know these problems well and know how to do them well. Any other questions? Yeah. Oh, you don't have to memorize. You won't have to memorize anything. Any formulas you need, including the first law of thermodynamics. You just need to know how to use that stuff. Yeah, thanks for asking that. So, I mean, I'll give you the first law. I'll give you the relationship between, yeah, I'll give you any unit conversions you need. You just need to have the practice of using this stuff, using, you know, how to put the equations together. I'll give you the definition of work equals to PdV. I'll give you all that stuff. Yep. Oh, yes. I meant to give that, but density I did give that actually, didn't I? I think that was in the notes, was it not? Okay. All right. Well, anyways, yeah. And if there's anything like that that I don't give, just come up and ask, and yeah, I'll put it up on the board or something. Density. Okay, so this is the end. Let's say this is the end of this. Density is 1 over the specific volume. So there's a reciprocal relationship between those two. And it has, so density has units of kilograms per meters cubed. Specific volume is 1 over density, and it has units of meters cubed per kilogram if you're in SI units. Yep. Yeah.
I was curious why the math just used
because so we're sort of used to thinking of, because you know what, why we think this way is because of bathroom scales have a switch that goes between kilograms and pounds, but pounds is really a force. Kilograms is a mass, so they're not equivalent. Your scale makes that conversion assuming the acceleration of gravity at sea level or whatever. So if you have something in pounds, that's the force. Oh, okay. I don't have that problem in front of me, I don't think. Oh, wait, I do. 7. Okay, so 2 pounds of gas. All right, so let's do number 7. This is in the intro. Okay, so we had 2 pounds of gas. And the process we know follows pressure times, this is capital V volume, so we know that's actual volume, that's not specific volume, to the N is equal to a constant. And we start with, so P1 is equal to 20 pounds. And if you uh, 20-pound force, that's being very specific about the fact that this is talking about a pound as a force. Okay, so, well, let's just go through it. Divided by inches squared. And at the end of the process, pressure is 100 pound force per inch squared. So those are the two pressures. And at the start, the volume is 10 cubic feet. And at the end, it's 2.9 cubic feet. What's the value of N? And was there one specifically that, oh, part B, you're asking about the specific volume? Okay, well, and I didn't divide by, okay, so we're gonna do almost everything in SI units, but here's how this problem would be written so that the way I did it is undeniably right. If you say that you have 2 pounds mass, you know, so this thing, I don't like that. I don't like that way of doing it. But since this is saying, since this is talking about pound force, we're making a distinction between the pounds as a mass of gas and the pounds as the pressure as a in terms of pound force. In other words, let's see, 1 pound force is equal to 1 pound mass times, the acceleration of gravity. Yeah, right. I will be much more explicit about that on the test. So it's a little ambiguous because I didn't say what this was, but there's a distinction between this type of pound and this type of pound because I called them different things, And so since this was given explicitly as pound of force, at least the way I was thinking of it was that this is a pound of mass. I hate that way of thinking about it though. So I'm like,
The more I think about it, you know what I mean?
yeah.
I mean, we have to.
I hate that pound force, pound mass thing. So what I would like a better way is if I would have just said they were all pound mass, and then you would have divided the to come up with the mass, you would have divided by the acceleration of gravity, and then so the way you're thinking is right.
Gives you different, like the pound mass. You think about it as like pound second squared over meters.
Yeah, whatever those units come out to be, right? Pound second squared over meters, or yeah, whatever units, right? Yeah, pound second squared over.
Actually, yeah,
Right. Right. You're right. And those come out with different answers, no doubt about that. The question is just the ambiguity of what kind of pounds I'm talking about here. Anybody have any more questions about that one? Okay. I try to put a few problems in different units than SI units because you'll see them, but I tend to, when I see something in imperial units, I tend to just convert it to SI units because that's what I like working with. So, and you can always do that. Anybody have any other homework questions? All right. So going back to the first law of thermodynamics, let me just kind of give a summary. First law of thermodynamics is the one that's conservation of energy. And it has this form: the change in energy of your system is equal to the heat Q minus the work W. That comes from the reason that we're subtracting W is because of the funny sign convention on W. Positive W means means energy is leaving the system through work, or the system is doing work. And the way you remember that is that this sign convention is related to what you do in a heat engine. You add heat to your system, the gas, and the result of heating up the gas is the gas doing work on the surroundings. You can expand this. The change in energy is equal to, so what are all the ways there can be energy in our system? There's change in, I'm going to just write it out like this, change in kinetic energy. So last time I was using that capital Z. This will be a little more clear, I think, what I'm talking about. Change in kinetic energy plus the change in gravitational potential energy. It could be any potential energy, but the only one we're going to deal with is gravitational. And by the way, in the majority of problems in this class, these are going to be 0. We're not going to have, not always, but we're not usually going to have cases where our system is changing speeds or changing heights. Okay. Plus the change in this new thing, capital U. And that's called the internal energy. And we don't have to know much about what that is yet. But often, like if you want an intuitive idea of what it is, it's usually connected to temperature in most cases. So if you have a change in energy, if your system is a gas and you have a change in energy of your system, that gas, you can get that whole body of gas moving. That would change its kinetic energy together. You could change the height of that gas. That would be the change in potential energy. Or what we're going to see almost all the time, or additionally to those, you could change the temperature of the gas. If it gets hotter, you have more energy stored inside the gas, more internal energy. And if it gets cooler, you have less. That's not 100% true, but intuitively, that's a reasonable way to think about it, changing the temperature. Because temperature is actually a measure of the kinetic energy of the individual molecules, like an average kinetic energy. Oh, so what's the difference between, so if this is basically measuring a change in kinetic energy of individual molecules, this is a change in kinetic energy. What's the difference between those two? This is just macroscopic. So this is like what you notice about, say, the center of mass of the gas. These are the individual molecules bouncing around. Okay, you don't see those macroscopically except through temperature. And we can expand these more. So the change in energy is equal to 1/2 times the mass times the change in the speed squared plus mg times the change in the height plus, for now, this is just a change in internal energy. But in specific cases, we'll be able to calculate this later. And then what about heat and work? So heat, later, actually in the next section, we'll know some things about heat transfer. But for now, that just has to be given as a number. And for those of you who are going to major in mechanical engineering, the next class that you'll take related to this will be entirely about heat transfer, where you're dealing with differential equations related to how heat is transferred. And work, well, there are a few ways that work can be done, but the most important for us is that work is equal to the integral of P dV as you go from volume 1 to volume 2. So putting it all together, putting everything we know together, we know that 1/2 times the mass of the system times the change in the speed squared plus mg times the change in the height of the system plus change in internal energy is equal to Q minus the integral of P dV from V1 to V2. That's a fully expanded form of the first law of thermodynamics.
Will we have to do the other ones?
Oh, for like rotational kinetic energy? For a spring? Potential energy? We, not in general. Problems might come up at some point, but, you know, for sure 95% of the time, we're only going to deal with gravitational potential energy. Probably, I'd say actually 95% of the time, we won't even have gravitational potential. There'll be a couple of problems that'll come up where you do spring potential energy. I don't think that ever comes up in any problems I assigned this semester. But it would, but I like that way of thinking, you know, like all of this stuff is expandable beyond what I have here, you know. All right, so let's do an example using the first law of thermodynamics. So let's say that we have, so our system is a 0.5 kilogram combination of a gas and its container, whatever that is. Um, 100 joules of work and 50 joules of heat are both added to the system. As those are added, the system goes from rest to 3 meters per second and is lowered 2 meters. What's the change in the system's internal energy? Okay, well, maybe you can already notice just from the stuff that's given that we're basically going to be going to a kind of expanded form of the first law of thermodynamics. We're not going to have to deal with the expanded, the integral equation for work, because we only do that to figure out what W is, and we're given W. But with work and heat, we are going to have to be careful with that sign convention, okay? Like, if work is added to the system, what does that mean? If heat is added to the system, what does that mean? So let's start with the simple one and sort of expand things out from there. We know that the change in energy is equal to Q minus W. 50 joules of heat is added to the system. Does that mean Q is positive or negative? Yep, in a heat engine, heat is added to the gas. So this is positive 50 joules. And 100 joules of work is added to the system. So right, work is negative 100 joules. And so we know that the total change in energy is equal to, careful because this is a negative, so this is 150 joules. Because if you think of what a heat engine does with the sign convention, a heat engine does work on the surroundings. Instead of this system doing work on the surroundings are doing work on the system. Okay, it says 100 joules of work are added to the system. Okay, so that means W is negative. Yeah, but because of the negative sign here, it's negative 100 joules, so it comes out to a positive 100. Yep. Actually, no, in this case, so this is the most basic, like what I usually think of as starting point for the first law of thermodynamics. And this is going to expand into change in kinetic plus change in potential plus change in internal. In this case, we actually are going to have non-zero. This will be one of the rare cases where we have non-zero change in kinetic and non-zero change in potential. So I'll expand that next. Okay, so we know that the change in kinetic energy plus the change in potential energy plus the change in internal energy is equal to 150. And we can write that as 1/2 times the mass of the system times the change in speed. The change in speed, it went from 0 to 3 meters per second, so this is 3 squared. Plus mgh, so that's the mass of 0.5 times 9.81 times the change in height. It lowers 2 meters. So what's the change in height? Yep, -2 plus delta U is equal to 150. So 2.25 minus 9.81 plus delta U is equal to 150. And so that's 7.56. Delta U is 157.56 joules. So as far as the first law of thermodynamics, all you're doing right now is playing sign convention games, basically. I mean, but I don't mean to say like it's unimportant. Like that sign convention stuff is going to continue to be a pain in the butt the entire semester, and it's totally crucial to everything we're going to do this whole semester. So you need to get used to thinking about when you're thinking about the sign convention for things, particularly Q and W. Keep that heat engine in mind. The heat engine, the gas expands, so energy is given away through work, and the fire or whatever, the boiler heats up the gas, so energy is added to the system through heat. Okay, and so that's where the sign convention comes from. Okay. I just have a few other example problems here that are related to the problems that are on the assignment you're going to see. So I wanted to go through these, but if you have any questions about them, for sure, let me know. Okay, so let's say that we have a gas that goes from a pressure of 2 times 10 to the 5th pascals. That can be written as 2 bar. And a starting volume of 0.3 meters cubed. And process takes it to a new pressure, T2, of 0.5 times 10 to the 5th pascals, or 0.5 bar. And a new volume V2 of 1.5 meters cubed. Now, say that we know through an experiment that the pressure throughout the process is going to be equal to A times volume to the D power. On a couple of problems in this set, it says something about this being known by treating the gas as a quasi-equilibrium, the process as quasi-equilibrium. That really isn't, that idea of quasi-equilibrium isn't really crucial to using what's given in the problem. But the idea of quasi-equilibrium is that things are happening slowly enough that you can imagine at every instant you're in equilibrium. You could stop there and nothing would change about the pressure or the volume, you know. And we want to know first, what's W? And second, like with all of these, does the sign make sense? Okay, so first of all, let's figure out what we expect from the sign. And how do you know? What's the sign of work going to be, and how do you know? It's just a simple matter of whether the gas contracts or expands. If the gas expands, you're going to have a positive W. If it contracts, you're going to have a negative W. It's as easy as that. So we start small and end big, so W has to be positive. All right, so now the hard part is calculating the work. And we know that work is equal to PdV. If we totally had our choice, if you were designing your own problem, you would make pressure constant. But unfortunately, there's a lot of times that things we want to calculate don't have constant pressure. Okay, well, then failing that, you need to have pressure. You need to know what the pressure is as a function of volume. We did an example problem like this last time with one little difference. Do you remember last time it was something like this? We had the pressure and volume at the starting point, and we only had one or the other at the ending point. We didn't have both. Okay, so what is that? And we had a different relationship here. Oh, it turns out that that's necessary in this case. Do you know why? What was different about the problem where we only knew one of the end conditions, and this problem where we need to know pressure and volume at both?
Temperature.
But actually, it's simpler than that. It's kind of right in front of you here. The difference is last time we knew everything about, so it was something like pressure is equal to A volume to a known power. So we had a relationship with only one parameter we had to solve for. So we didn't need as many equations. We needed one equation to solve for that one parameter. Now we have an A and a B, so we need two different equations to solve for the two parameters. And that equation could look like anything, it could be sine of A times volume, or a linear function. But if you have two parameters you're solving for, you're going to need both of the pressure and volume at both spots. Okay, so to solve this, we're just going to, it's basically a system of two equations for two variables. So at state one, plug what we know into this relationship between pressure and volume. We have 2 times 10 to the 5th is equal to A times 0.3 to the B Everyone see where I'm getting that? And then state 2, you have the new pressure, 0.5 times 10 to the 5th is equal to A times 1.5 to the B power. So there's your first equation and your second equation. You know, I'm not going to make these too hard to solve because this isn't supposed to be an algebra class or whatever, but let's see. From this one, we know that A is equal to 2 times 10 to the 5th times 0.3 to the negative B. Now plug that into equation 2, and you have 0.5 times 10 to the 5 is equal to 2 times 10 to the 5 times 0.3 to the negative b power times 1.5 to the b power. And divide both sides by 2e to the 5, and you get 0.25 is equal to 1.5 to the b divided by 0.3 to the b. And so 0.25 is equal to 5 to the b. So natural log of 0.25 is equal to b times the natural log of 5. So b is equal to the natural log of 0.25 divided by the natural log of 5. And I think you get negative 0. Oh no, it's b is equal to 0.861. B is equal, it does come out negative, yeah. Negative, oh yeah, wait, it does. B, negative B, okay. So that's negative. And why did we do all this? What were we trying to find? We're trying to find pressure as a function of volume. So pressure as a function of volume now is equal to, oh, we have to plug that back in and get A. So we can use that to say that A is equal to so can someone calculate that? 2 times 10 to the 5th times 0.3 to the positive 0.861? Okay, so pressure as a function of volume is 70,930 times volume to the negative 0.861. And now the work is equal to the integral of the pressure times the volume. So that's the integral from V1 to V2 of 70,930 V to the negative 0.861. That's the pressure, and then times dV. So that's equal to 0.139. So 70,930 times V to the positive 0.139 divided by 0.139, evaluated from our starting volume of 0.3 to our ending volume of 1.5. What? Yeah, I just did the integration for like a polynomial term. And anyone have a calculator that'll do that? $226,000 what? 447 joules. Does the sign of the work, does the sign of W match what we expected? Yeah, the gas is expanding. Any other questions about that one? Okay, let's do one now where we're dealing with intensive properties. Okay, so let's say that we have a cylinder and a piston. And the piston is this giant heavy thing with a mass of 5 kilograms. This is the gas. And let's say that we have 0.1 kilograms of gas. And it goes from a specific volume, V1, so that's a lowercase v, of 0.5 cubic meters over kilograms, to a specific volume, V2, of 0.3 cubic meters per kilogram. the only thing pushing on that piston is atmospheric pressure on the outside. So we can use that to figure out anything we need to about the pressures. And we want to calculate, so first the area of piston, let's say is 0.02 meters squared. So first, what's the pressure of the gas? And second, what's W for the process? So the idea is that both of these two volumes are at equilibrium. We do something to the gas to make this happen during the process. The specific volumes go down. Since the mass stays the same, that means that the true volumes go down, right? And so if the volumes go down, what are we doing to the gas to make that happen? Yeah, and how are we making that happen? Because we could make it happen by changing atmospheric pressure, but that's hard to do. So what's an easier way to do it? The temperature, yep. So you cool this down, the gas contracts, and the volume produces. And then if it's contracting, what's the sign of W? Negative, yep. So we expect when we calculate W to get a negative sign. Okay, so first, what's the pressure of the gas? Anyone have an idea of how to calculate that? So you could, if you know something about the gas, you might be able to use properties of the gas to do it. But we're just going to use the fact that it's in equilibrium at both of those 2 points and isolate the piston, okay? Because we know what forces are acting on the 2 sides of the piston. So, right. So, free body diagram of the piston. So here it is from the side. So what's acting? Well, it's a big, heavy thing, so we're not going to want to ignore the weight. So the weight is 5 kilograms times 9.81, 49.05 newtons down. And then atmospheric pressure pushes here, and it's equal to 1.01 times 10 to the 5th times the surface area of the piston, 0.02. And then pushing up, we have the pressure of the gas that we're trying to find times the surface area of the piston. Yep, Newton's second law, exactly. So Newton's second law says, I'm going to say positive is up, so 0.02 times the gas pressure minus 0.02 times, this comes out to be 2020 if you multiply 0.02 times 1.01 times 10 to the 5th, and then minus 49.05 It's in equilibrium, so there's no acceleration. Now you can solve for the gas pressure. And you get 1.0345 times 10 to the fifth pascals. So pressure in the gas is a little bit bigger than the atmospheric pressure because the gas has to support not only atmospheric pressure but the weight of the piston. And was this at the beginning or the end? Both. If you look at what I put in, we didn't use anything about the volume, and so it's totally general. Like, since both of those two cases are in equilibrium, the pressure is constant through the whole process, which is great when you're calculating work, you know? So if you see that on the test, you're like, yeah. You know, but don't do that during a test because that distracts people. So anytime that you have a piston that's just being pushed down on by atmospheric pressure, no matter what happens during the process, the pressure of the gas is constant. So what do we need now? We calculated the pressure, so now we just have to calculate the work. So the work is equal to the integral from, so before we do this, so the whole idea of this problem was to show what to do if you're given stuff as intensive properties. Well, the work is equal to P EV, but we don't have big V yet, you know, from V1 to V2. Big V is equal to the specific volume times the mass. And so V1 is equal to, big V1 is equal to 0.5 times 0.1, so 0.05 meters cubed. And V2 is equal to 0.3 times the mass, 0.1, and that's equal to 0.03 meters cubed. And now we're ready to do the integral. By the way, like, why ever deal with specific volumes, or what's the point of these intensive properties? Well, we're going to see that the equations of state that we're going to use a lot, and a lot of what we can think of as equations of state, we're just going to read off of tables that are given to us. Those quantities are given in terms of intensive properties because they want to be general for however much material you have. And so, especially once we start using tables, in a week or two, we're going to have to go from intensive properties to extensive properties in like every problem. Okay, so work is equal to the integral from the starting volume to the ending volume. And from that, you can see where the negative work that we're looking for is going to come from. Times that constant pressure, 1.0345 times 10 to the fifth dV. And that's equal to 1.0345 times 10 to the fifth times 0.03 minus 0.05. And you get 2,069.04 joules. And get in the habit of just always looking at that sign and saying, does it make sense? From the beginning and ending volumes, you can tell what the sign of the work should be. No. And that didn't make sense, so good thing I did that. But now it makes sense. Any questions about that one? Okay. This one is a lot like number 10, I think. Okay, so let's say that we have a setup, cylinder piston setup. From the side, it looks like this. So we have a gas in here. We have a piston, and that piston is connected to a spring. Let's say that the mass of the gas is 0.02 kilograms. And the specific volume goes from 0.001 cubic meters per kilogram to 0.002 cubic meters per kilogram. And the spring force varies linearly with volume. So there's a linear relationship between the volume and the spring force. From 0 newtons at the first state to 10,000 newtons, that's a strong spring, at the second state. Let's say that the piston cross-sectional area is 0.1 cubic square meter. It's an area. And the atmospheric pressure is 1 bar, or 1 times 10 to the 5 pascals. We're going to assume that this process is quasi-equilibrium, quasi-static. Process. And we want to know first, what are the beginning and ending pressures? And second, we want to know what's W. All right, so when we get to W, what's the sign going to be? It's expanding, so it's going to be positive. But like, what about the spring? Like, this is a more complicated setup and all that. It doesn't matter. If the gas expands, W is positive. If the gas contracts, it's negative. Quasi-equilibrium says that at the beginning and ending pressure, we can assume that there's no acceleration. So we can use that in Newton's second law to figure out the pressure in the gas. How can I make this problem harder? I can make this problem harder by just not asking part A. You see that? Because to calculate W, you need that integral that includes pressure in it. And that would make you recognize that first you have to calculate those pressures in order to, in order to calculate W. This is sort of stepping you along the process. Okay, so what are the beginning and ending pressures? So state one. Let's isolate the piston. At state one, there's no force provided by the spring. So the only force pushing down is 1.0 times 10 to the fifth times the cross-sectional area. And the force pushing up, I didn't give a mass, by the way, of the piston. That just means that it's small. We're neglecting it. The force pushing up is 0.1, that same cross-sectional area times the pressure of the gas. Newton's second law says those have to be equal. So P1 is equal to 1.0 times 10 to the 5 after you go through that. And then free body diagram of the piston. At state two. Now we have the spring force pushing down of 10,000 newtons. In addition to the force applied by the atmospheric pressure. And then if that's equal and opposite to 0.1 P. So Newton's second law says 0.1 P minus 1.0 times 10 to the 4 minus another 1.0 times 10 to the 4, the 10,000. Is equal to 0. There's no acceleration. And so the pressure is twice as big, 2.0 times 10 to the fifth. So that's P2. Now, what we're going to is, this is the third example of a problem like the first one I did in class today, where we know a kind of relationship between pressure and volume. We're going to need that pressure as a function of volume to integrate to get the work. And we have a system of equations to solve for the parameters. We know that the pressure is, well, the force, and therefore the pressure is linear in the volume. Okay, we know that pressure is equal to, m times the volume plus b. And so now we're going to use what we know at state 1 and state 2 to come up with those parameters. V1 is equal to, I'm not going to finish this problem, but I'm going to hopefully just get it to a point where you can tell where to go. So we have the total mass, 0.02, times the specific volume of 0.001. Hi, we're almost done. And that's really small, 0.0000 0.00002. That's why you use scientific notation. Volume 2 is equal to 0.02 times 0.002. So that's 0.00004. And now you know, let me just sort of describe what's going on. Now you know P1 and V1 and P2 and V2. Calculate the parameters M and B. And then you can do the integral finally. V1 to V2. Okay, so send me an email if you have any questions about that, or else we can talk about it on Monday. But this is basically just different numbers, but number 10 from the problems that'll be assigned. Yeah.